Start with the session anyways. So last class we just started looking into non-ideal reactors. So we looked into what all reasons there can be for non-ideality. So we looked into things like bypass and channeling and so on. And then we looked into what is called as the residence time distribution, or RTD. So we look into what is called as a residence time distribution or an E curve, and we look into how we can find the moments of RTD, like the mean residence time T bar, or the variance, which is sigma squared, or the skewness SQ. So we had like a lot of straightforward formula for that, and we basically I think we even solved one problem where we wanted to find the mean residence time and so on. So we solved a few problems as well based on the concepts with regards to the residence time distribution. And all these things are applicable for pulse input or a single shot input. So we mentioned there were a lot of different kinds of inputs for a reactor. So just to mention a few, if you have a reactor and you are giving an input, you can either give it in the form of a pulse, which will be like a single shot at time, let's say t. You just introduce a whole lot of your tracer at time t, and that is known as a pulse input, or it can be something like a step input. So at step input, you inject a unit amount of input at time t, or it could be something like in a waveform. So you can have input like this, or you can even have something like a ramp. So let's say from time t, you just gradually increase the concentration of your tracer. So these are just like the different kinds of inputs that you can give. And last class we basically focused on pulse input. So this class we'll look briefly into the step input, and from then on we'll try to give a brief introduction to catalysis as well. So most probably we won't be solving any previous gate problems this class. We'll try to like look into the concepts first, and if possible, of course, we can try solving problems. But anyways, let's move on to the step input. So again, let's consider a PFR, and let's say we have an input and we have an output from the PFR or the peripheral reactor. And last class was basically, to just summarize last class, this was the thing. So if we have an input like this, the pulse input, and we can get the, this is just C versus T plot. If we give an input like this, the output, if we plot it, you know, C versus T, we'll get something like this. And this was not, and from this we got the residence time distribution. Now, instead of pulse input, if we put something like a step input, so this is the input. Let's say this is C max or C step, or you can even say it as the C step. So if we have an input like this, the output will become something like this, where this will be the C0 or C max or C step. So basically, this C versus T curve is from where we derive our RTD for pulse input, and the analogous to the E curve that we derived for the pulse input. Here we can get something called as the F curve, which is analogous to the residence time distribution, but for a step in, right? So in this pulse input, we had the residence time distribution E as C by integral 0 to infinity C dt, where this integral 0 to infinity C dt is the area under this curve. The same way, we can write for step input, F will be C by C0. So again, F here is basically nothing but the fraction of material leaving the reactor. Right. So how do we draw an F curve? We just use this concept here. So we have F is equal to C by C0. So if we just plot something like this, T, and instead of C on the y-axis, we just take the C by C0, and that is basically is equal to F. So that will be from 0 to 1, and the curve will follow like this, where the maximum value of F would be 1, because fraction can never be greater than 1, and F is basically just a fraction of material leaving the reactor at a given time. So this is basically the F curve. So one of the basic relations that we can have for an F curve, from the C curve, we can write C, or the outlet concentration C, is equal to C0 into 1 minus e raised to T by T bar. Okay, where T bar is the usual one, mean residence time. So this is one of the basic relationships that we can get from the C curve for a step input, which is C is equal to C0 into 1 minus e raised to T by T bar. And we can also have this relation, we had this relation F is equal to C by C0. So T bar will be integral 0 to infinity T into Tf. Oh, sorry, not 0 to infinity, this is 0 to 0 to 1 Tf. Well, that means, if we have an F curve like this is 1, this is 0, and this is T. The area here is the mean residence time. Fine. So to find this area, there is one thing that we can. There is one more thing that we can do. Let's say so let's say this is our residence time T bar. So what we can do is, instead of finding this area colored in red, which is basically your mean residence time, we can also find this area, and this area will also be the mean residence time, right? Because this is basically a rectangle, and the area is side by side into side, but one side, this unit is basically 1. So whatever this unit is, which is T bar, so 1 into T bar will be the area, and that is basically T bar. So that is the gist here. So this is just a graphical method to find the mean residence time from your F curve. but the integral to find the mean residence time is given here. Another way we can represent this f curve is like this. We can plot, instead of plotting f versus t, we can plot 1 minus f versus t, and that will be like this. And again, this area will be mean residence time t bar. Right. So, what is the relationship between your E curve and F curve? So let's see this. So let's say you have an E curve, and again you have an F curve like this. Now both these E curves and F curves represent the fraction of material that is leaving the reactor at a given time, right? So let's say we are trying to find the fraction of material leaving the reactor at, let's say, time t1. So you can just extend it to this f curve, and you can find the corresponding value of f here using this extension. So let's say 50%, this area is basically 0.5 or 50%. Then if you extend it from this E curve to the F curve, you will get some value here. Just for the simplicity, we'll just say this is 0.5. So you can extend this E curve to the F curve like this, because both of these represent the fraction of material leaving the reactor at a given time, and that time here is t1, right? So basically, if you want to represent the relation between the E curve and F curve using some equation, you can simply denote the f, or the fraction leaving the reactor at time t, using an integral 0 to t1 e into dt. Now the reverse of this is basically e will be df by dt, right? So this is the fraction. This f will be the fraction of material leaving the reactor at time t1. Now, if f is the fraction of the material that is leaving the reactor at time t1, then what will be the fraction that is still inside the reactor? So, if this much fraction has left the reactor, that means this fraction is still inside the reactor, and that can be represented as 1 minus f. And 1 minus f will basically be what? Integral t1 to, let's say, there's a resistance time ends at t2. So t1 to t2 e into dt. So this will be the fraction remaining inside the reactor. Right? So this is like a relationship that you can derive between the E curve and the F curve. So we looked at the basics of E curve and F curve. Now let's try to apply this residence time distribution to EFR and CSTR. So let's see what is the RTD in a PFR. So RTD in a PFR, this can be represented by a delta Dirac function. That is basically E can be represented as delta of T minus tau p, where tau p is the space time of the PFR, right? So integral 0 to infinity E of t dt will be 1, right? Because area under the E curve is always 1, and this will be equal to integral delta of t minus tau p 0 to infinity. But one of the assumptions that we did for PFR, or an ideal PFR, is that the residence time for all the molecules inside the PFR is same, right? So if a molecule enters, if a group of molecule enters the PFR like this at time, let's say t equal to t1, all these molecules will exit the PFR at the same time. Let's say which is t2, right? So this is one of the assumptions that we made for an ideal PFR. So a residence time in a PFR is basically the space time of this PFR. So which basically means T will be tau p, or the space time of the PFR. So that means at this point E will be 0. Or in other words, you can just say there is no distribution in a PFR. Right? But if we go for a RTD in a CSTR, we didn't make any such assumptions like this. So you can definitely get an RTD in CSTR. Now RTD in CSTR can be represented by two equations. So let's just pictorially represent this. So this is a CSTR, and let's say you have C0 as the initial concentration of your tracer and C as the final concentration. You can write the outlet concentration as C equal to C0 e raised to minus T by tau m, where tau m is the space time of CSTR. Okay. Now using this, we can find your RTD as E equal to 1 by tau m e raised to minus T by tau m. So this will be your residence time distribution for a CSTR. Okay. So yeah, just make a note of these two equations, because what we'll do now is we'll try to find an equation for RTD in a multiple reactor system, like where a CSTR followed by a PFR, or a PFR followed by CSTR. So I hope you noted these equations, and if then we'll just move on. So now we have we know the behavior of RTD in a PFR and CSTR. Now let's say if you have a system like a PFR followed by CSTR. In this case, let's just represent this. So let's say C0 is our inlet concentration. C1 is the outlet concentration from a PFR. PFR, and C2 will be the outlet concentration from a CSTR. Or actually, take the inverse case. Just for So we'll take the case of CSTR followed by PFR. So we have a CSTR. This is followed by a PFR. So let's say the inlet concentration into the CSTR is C0. The outlet concentration of the outlet concentration from the CSTR, let's say as it is C1, and the outlet concentration from the PFR is C2. So E1 will be the resonance time distribution at the outlet of the CSTR, and E2 will be the resonance time distribution at the um, outlet of the PFR. Fine. So we had the basic equations for RTD of CSTR and PFR. So we'll just use this equation for the concentration as well as the resonance time in the next case. I mean the multiple reactor case as well. So we had the equation, C equal to C0 e raised to minus T by tau m for CSTR for your outlet concentration, and we had the resonance time distribution equation as 1 by tau m e raised to minus T by tau m. So we'll just use that in the next case. So then C1 will be C0 e raised to minus T by tau m, and E1 will be 1 by tau m e raised to minus T by tau. Right? So this will be the outlet concentration and the resistance distribution at the outlet of the CSTR. Now this C1 or the C1 will enter your PFR, right? So what we learned in the last case was that the resonance time distribution for a PFR is basically a delta Dirac function. So long story short, your concentration will become something like this: C0 e raised to minus T minus tau P by tau. Because your resonance time will get affected by the PFR, and consequently your resonance time distribution E2, which is the final resonance time distribution for this CSTR followed by PFR case, and that will be 1 by tau m e raised to minus T minus tau P by tau. So this is basically your final resonance time distribution of a CSTR followed by PFR. Okay. Now the peculiar thing is, this is same for the reverse case, which is PFR followed by CSTR. Okay. Now let us let us try to draw the E curve for this system. I think we briefly saw how the E curve will turn out for a PFR followed by CSTR case, but just let us see how we arrived at that resonance time distribution. So we have this equation, okay, this E2 or the resonance time distribution for a CSTR followed by PFR case as E equal to 1 by tau m e raised to minus T minus tau P by tau m. Now, when T equal to tau P, what happens is this whole term, the exponent term, will be e raised to 0, and that will be 1. And at that time, E will become 1 by tau m. So that is how at tau P, T equal to tau P, the RTD at this point will basically be like this. And the y-intercept for this is 1 by tau m, which is E. Okay. And from then on, as tau P is greater than T, your RTD will come like this. So this is how we got the RTD for a CSTR followed by PFR system that we briefly saw in the last class. So this is just the basic, of that article, right? And as I said, this scenario is same for both PFR followed by CSTR as well as CSTR followed by PFR, right? So is this clear? I just briefly went through the results and distribution concepts for non-ideal reactors. Um, yeah, is this understandable? Is this clear? Or if anyone has any doubts, you can always unmute and ask, or type it in the chat, whichever you wish. Fine. If that is the case, then we'll go to the catalysis part. We want to just see some of the basics of the catalysis as well. So initially, what was planned was we'll try to finish CRE by one or two more classes, but I don't know how feasible is that. But anyways, let's try. So anyways, if this is clear, then we'll move on to the catalysis part. So, CRE, most of the syllabus is basically dividing this chemical reaction engineering into two different semesters. So one will be CRE one and the other will be CRE two in most of the universities. So CRE two is basically the two main chapters in CRE two is non-ideal reactors and catalysis. So we just looked into some of the basics of non-ideal reactors. We'll try to look into catalysis as well. So before we go into anything detailed, what is a catalyst? So a catalyst is basically something that makes the reaction go faster, or that means that makes makes the reaction go faster, or in other words, increase the reaction rate Rn. And how this is achieved? By lowering your activation energy. Okay. So, how a catalyst works, we'll see that briefly as well. But before that, I want to introduce you guys to one more term: active sites. So, active sites are the place on the catalyst where reactants bind and undergo reaction. Okay, so let us just consider the simple reaction. A gives B. Okay. So let's say we have a catalyst like this, and catalysts are usually not smooth surfaced. So we have something like this, and this is your reaction medium. Okay. Okay, so this is basically filled with A, your reactant molecule A. So what happens is this A will come in contact with your catalyst and binds at a point, and this point is called as the active site. So these are all these can be active sites. Okay, and at this point your reaction occurs. So this reaction occurs, A gives B at an active site. And once that happens, your B will just diffuse out of this active site and go back into the medium. So this is like a very simple way of putting how catalyst or a catalytic reaction occurs. Now there are a lot of different steps involved in a catalytic reaction. So there are basically 7 steps involved in the catalytic reaction. We'll see each one of them one by one. So this is like a basic picture of how a catalyst works. So you have a reactant. That reactant will go and get adsorbed onto an active site on a catalyst surface, and at that active site your reaction occurs, and then your product molecule, which is B here, will get desorbed out of the active site, and it will go back into the bulk medium. Right. Now let us try to zoom in on this. So let us say, let us just take one active site like this. Okay, so you have A in the medium. First, what this A has to do is first get diffused to the surface of your catalyst. Okay, so that is the first step. That is external diffusion from bulk medium to catalyst surface. Okay, so this is your first step in a catalytic reaction. Now, the second step, once this reactant molecule reaches the catalyst surface, it has to now get into your active site. So that is the second step. So this is an active site. So from this, and this is the surface. So once it reaches the surface, now it has to get to an active site, and that is the second step. So the second step is basically internal diffusion of your reactant molecule, which is A here, A from the external catalyst surface to the internal surface of the catalyst, which is basically your active site. Now once it reaches this active sites, there are 3 things that happens here at the active site. The first thing is it should get adsorbed by the active site, then your reaction will happen, and then the products should get desorbed. So the 3 things happens at the active site. So these are the next 3 steps in your catalytic reaction. So the third step is adsorption of your reactant A on the catalyst surface or active site. Then your fourth step is your reaction that happens. The reaction here is basically A gives B. Right? And the fifth step is the desorption of your products B from the catalyst surface or their active site. Okay, and once once your products are formed, now your products has to just leave the catalyst area and go back into the bulk. So that is the next two steps. The sixth will be, internal diffusion that happens for B of B from the active site to catalyst external surface. And finally, say some this will be external diffusion of B from the external catalyst surface to the bulk medium. Right. So these are the seven major steps involved in the catalytic reaction. So first your reactant has to reach the catalyst surface, which is step one, and then it has to find an active site, that is step two, and it has to get adsorbed. Then the reaction proceeds, and then it has to get desorbed. So these are step 3, 4, and 5. And once your products are desorbed from the active site, it has to then undergo an internal diffusion to reach the catalyst surface, that is step 6. And then from catalyst surface, it has to undergo an external diffusion to reach your bulk, and that is the step 7. Right? So these are the 7 major steps that is involved in the catalytic reaction. Clear? Now, since there are multiple steps that is involved in this catalytic process, what we usually not assume, we can actually say, is that the slowest step out of these 7 different steps will be the rate determining step. Okay. So you have 7 different steps. Whatever step is the slowest step, that will be the major contributor towards the overall rate of your catalytic process. Or in other words, the slowest step out of these 7 steps will be your rate determining step for the catalytic reaction. Okay, so that means any one of these 7 has the possibility to be the rate determining step for a catalytic reaction. So that is what the rest of the catalysis part deals with. So so you'll have 7 different scenarios where each one of them will be the rate determining step, and you'll have to find how you can find the rate of the reaction or what are effects it has towards the overall process by becoming the rate determining step. So that is basically your rest of the catalysis part. So let us slowly see how we can derive the rate equation for some of these scenarios. Okay. So let us divide this into 3 scenarios. So scenario 1, both the diffusion steps are fast. That means the other 3 steps, which are adsorption, reaction, and desorption, any one of these can be rate determined. Okay, this is scenario one. So both your internal diffusion as well as external diffusion are very fast, and because of that, your rate determining step can be either your adsorption or the surface reaction or the desorption step. So any one of these can be the rate determining step in this scenario. Then we can have another scenario like this, where all your steps except external diffusion are fast. So that means external diffusion is rate determined. So that means internal diffusion, adsorption, reaction, as well as desorption are fast. Yeah. So that is scenario 2. And we can have a third scenario. In this scenario, your internal diffusion is rate limited. So that means all your external diffusion, adsorption, reaction, and desorption are very fast. So these are like three basic scenarios that you can have, in a catalysis reaction. So the first scenario is both the diffusion steps, the step 1 and 2 and the 6 and 7. 1, 2, 6, 7. All these steps are very fast. So your adsorption, which is step 3, reaction, that is step 4, and desorption, that is step 5. These three things, any one of these things can be the rate determining step, or any one of these steps can be the slowest step in the process. And the other two scenarios where one scenario says your external diffusion can be the rate determining step because that is the slowest step, and the other final scenario says your internal diffusion can be the rate limiting step, and all the other steps are very fast. So we'll have to look into these scenarios one by one as a different case. Okay, fine. So let us first deal with scenario 1. So here your diffusion steps are very fast, and that means your adsorption or reaction or desorption, any one of these can be your rate determining step. Okay, so this is the scenario 1. Fine. Let us take a very simple reaction like this. A gives B. Okay, so here we just said the diffusion steps are very fast, so we don't have to consider the internal and external diffusion steps. So here basically we only have 3 steps, The first step is adsorption. Second step is reaction. And third step is the desorption. Okay. So, right. So the first adsorption step, let us represent our active site as S. Okay. So active site, we can represent this as S. So total number of active sites will be CT. Total number of active sites. And let's say, let's say there are 100 active sites in the catalyst. It is not a necessary thing that all these 100 active sites will get occupied by a molecule. Some of these can be vacant, and only some of these will be occupied by a reactant molecule. So let us take the concentration of vacant active site as CV. So CV is the concentration of vacant active sites, and CT is the concentration of or the total number of active sites. Okay, so just these two notations, it's better to keep in mind. So anyways, let us start with the first step. The first step is adsorption. So adsorption means your reactant A will get adsorbed onto a catalyst active site, right? So if you want to represent it, we can represent it like this: A plus an active site S will reversibly give your adsorbed reactant molecule AS. Okay, so you can represent your adsorption step like this. Now the second step, in a similar way, you can represent your second step also like this. So your adsorbed reactant molecule AS will undergo reaction on the catalyst surface of the active site and will form the adsorbed product molecule BS. Okay, again, just to remind you, S here is the active site. Okay, just the notation of the active site. So A plus S reversibly giving AS is the adsorption step. Then AS reversibly giving BS is the reaction step. Now once the reaction happens and the products are formed, now the final step or the only remaining step is basically just desorption. So this product BS has to desorb or leave the active site and become B, and your active site has to go back to being an empty active site as S. Okay, so these are the three steps that you can represent it when the diffusion steps are very fast. The scenario 1 is what we are talking about basically. So there are three steps here in scenario 1: adsorption, reaction, and desorption. So you can represent these three steps as I just written here, as I just wrote here. And the thing is, any one of these can be rate determined. Okay, so that is the thing with scenario 1. Now let us assume the first step, adsorption, is rate determined. Okay, if I'll just write it this. If the first step, adsorption, let us represent the rate of adsorption as minus RA. Okay, that would be confusing. So if we take R adsorption as our rate of adsorption, and let us say this is the rate determining step, then desorption which let us represent it as minus R desorption, and the surface reaction, let's say, which we will represent as minus R reaction. Both these things will become zero. Okay, that means minus R desorption or rate of desorption will be equal to zero, and rate of reaction will also be equal to zero. Okay, so that is how we try to determine the overall reaction rate of this process by equating the non-rate determining steps as zero. Okay, so again, just to repeat it, diffusion, the external diffusion and internal diffusion has no effect here. Only these three, adsorption, desorption and reaction, can have an effect here. And just for an example, if adsorption is the rate determining step, the rate of desorption and rate of reaction will be zero. Now you can write this the other way as well. If rate of reaction is rate determining, then rate of adsorption as well as rate of desorption will be equal to zero. And if your rate of desorption is the rate determining, I will write that. If rate of desorption is rate determining, then rate of adsorption as well as rate of reaction will be equal to zero. So this is the general thing when we have the internal and external diffusion having no effect on your catalytic process, but any one of the adsorption, reaction or desorption can be the rate determining step. So at a time any one of these only can be rate determining step. So if adsorption is rate determining, then desorption and rate of reaction will be zero. So what do you mean rate is equal to zero? That means these are in equilibrium. Okay. So basically, if we just rephrase this, if adsorption is rate determining step, then desorption and reaction rate will be in equilibrium. Okay, because these are all reversible reactions, right? So this is we have a reversible reaction with rate constants K1, K2. Your reaction is also a reversible reaction. Your desorption is also a reversible reaction. Okay, so if adsorption is rate determining, then this will be in equilibrium. Okay, so that is what we mean by rate is equal to zero. So if adsorption is the rate determining, then desorption and reaction will be in equilibrium. If reaction is rate determining, then adsorption and desorption will be in equilibrium. And if desorption is rate limiting, your adsorption and reaction rate will be in equilibrium. Right? Now, let us divide these into three cases. So this adsorption being rate. So this case one, adsorption in equilibrium. Or what we'll do is we'll look into these things one by one. So let us look into adsorption first, then let us look into reaction. and then let us look into desorption. Okay. So let us take adsorption first. Okay. So adsorption, okay, it can happen in multiple ways, but let us just take the general case like this. So again, we'll take the simple reaction A gives B. Or just for an example, we'll take the oxidation of carbon monoxide. So carbon monoxide plus half oxygen. Okay, I don't think we don't need this. Okay. So let us take the reaction like that. So yeah, carbon monoxide given carbon dioxide. Okay. So carbon monoxide plus half oxygen basically. O2 gives carbon monoxide. So let us say this CO can get adsorbed onto the active sites in two ways. So the first way is, let us say this hill represents an active site. CO is basically C triple bond O, right? So both this C and O can get adsorbed here in a single active site. So that is something called as a single site mechanism or a single site model. Okay, and or this can get adsorbed into two different active sites. C can get adsorbed here and O can get adsorbed here. Right. So there are two ways where which this CO can get adsorbed onto your active sites. Now let us just consider this case. The first case, the single active site case. CO will get adsorbed onto a single active site to give you COS. Okay. So if you want to write the rate of adsorption will be, and this is a reversible process. So and the K1 and K2. So the rate of adsorption will be K1 concentration of C0 into concentration of S. S is the vacant site, and we put the notation as CV, C vacant site, minus K2 into concentration of the adsorbed reactant molecule. Okay, this will be your rate of adsorption. Okay, now if you want to, for the same scenario, if you want to, fine, let us take it like this. Now let us say if we have a situation where desorption or rate of reaction is in equilibrium. Is the rate determinism. So let's say desorption or reaction are rate determining step. So any one of this desorption or reaction can be the rate determining step. What that means is absorption will be in equilibrium, right? So that means minus RA will be K1 C0 into CV minus K2 C0S will be equal to 0. So this is what you mean by your adsorption being in equilibrium. Now the thing with this is, to determine this CV and C0S, it is a very complex procedure. Okay, because we can determine your reaction rate, the reactant concentration or your product concentrations experimentally, and there are a lot of straightforward methods where you can determine your reactant and product concentrations. But to determine the concentration of your active sites, the CV or CCOS, which is basically your reactant molecule getting adsorbed onto an active site. These are pretty difficult. Okay, so what we can do is we can try to find ways to eliminate these terms from your reaction rate equation, from the rate determining step. So that is basically how we proceed with such cases. So anyways, while working out this example, I hope you will get more clarity on this. But anyways, let us proceed with this case here. Adsorption being in equilibrium. So if adsorption is in equilibrium, this minus Ra will be K1 C0 into Cv minus K2 C0S COS will be equal to 0. Okay, that means K1 C0 into Cv minus K2 C0S will be equal to 0, or K1 C0 Cv minus K equal to K2 C0 COS. Okay. Now we want to find a term for C0 COS. So this COS will be K1 by K2 into CCO into Cv. Okay. Now we need to find a term for Cv, because as I said, determining this concentration of your vacant active sites is pretty difficult. So what we will try to do is we will try to use the site balance, active site balance and try to find a term for Cv. Okay. So what is this active site balance? This means basically your total number of active sites will be equal to number of vacant sites plus number of sites where your reactant or product gets adsorbed. Reactant is adsorbed. Okay. Or this basically means Ct, which is the concentration of your total active site, will be equal to the concentration of vacant site Cv plus concentration of sites where your reactant molecules are adsorbed. So that is CCOS. So rearranging this, we will get Cv is equal to Ct minus CCOS. So this is a site balance for this case. Okay. So if we have multiple reactants getting adsorbed onto the active sites, the site balance will change accordingly. So let us say if we have A, B and C getting adsorbed into AS, BS and CS, then the site balance will be Ct is equal to Cb, which is the vacant site concentration, plus CAS plus CBS plus CCS. And if you have an inert substance in the reaction as well, let's say inert I, and that is also getting adsorbed onto your active site and becomes IS, then you'll have to add that term as well, the CIS. Okay, so this is the site balance that we want to use to eliminate this Cv term. Okay, so here, so we'll write a site balance here. So here Cv will basically be Ct minus CCOS. Okay, so if we substitute that here in this CCOS equation, this will become CCOS is equal to K1 by K2 CCO into Cv, and that is Ct minus CCOS. So now there are CCOS terms on both LHS and RHS. So what we need to do is we just have to rearrange this. So CCOS is equal to K1 by K2 CCO into Ct minus K1 by K2 CCO into CCOS. So just bring it this side, it will become CCOS into 1 plus K1 by K2 CCO. That is equal to K1 by K2 CCO into CT. Okay, and note that K1 by K2 or the reaction rate constant for the forward reaction by the reaction rate constant for the backward reaction is nothing but your equilibrium constant K. Okay, now we just rearrange this and apply this K1 by K2 equal to K. We'll get CCOS equal to K CCO CT by 1 plus K CCO. Okay. Now we can also represent this in terms of partial pressures. That will be, CCOS will be K into PCO to PT by 1 plus K into PCO, where this PCO is the partial pressure of CO and PT is the total pressure. Okay, that is actually inaccurate. So we can have so we cannot say PT as the total pressure. In fact, it is not exactly correct to represent that in terms of pressure as well. So we only represent our reactants and products in terms of partial pressure. So this is in terms of partial pressure. Okay. So this is the term for CCOS for when your absorption is in equilibrium. Now, one more thing we can do here is so we have a term CCOS is equal to K into CCO CT by 1 plus K CCO, right? So this is the term for CCOS. We can apply this to your vacant active site concentration CV as well. And CV was CT into, CT minus CCOS, right? So that is CT minus KCCO into CT by 1 plus KCO. CCO. So that means CT into 1 minus KCO by 1 plus KCO into T. So this will be 1 plus KCO minus KCO, so CCO by 1 plus KCC. So this will get cancelled and this will become CT by 1 plus KCCO. This will be your term for vacant site. Okay. So, any doubts so far? So these are all just like basic reaction kinetics concept that we are applying. So for a reversible reaction, your overall rate will be the rate of forward reaction minus rate of backward reaction. That is what we applied here for this adsorption step. So yeah, but yeah. Anyways, just saying. So this CO plus S is the forward reaction, and your COS giving CO plus S will be the backward reaction. So we are just applying the basic reaction kinetics concept for a reversible reaction in this adsorption case. And we are just proceeding and we are just trying to eliminate the terms CV and COS. So that is what we have been trying so far, to eliminate these two terms from your rate equation. And we finally found the terms CCOS and CV in terms of CCO and CT, which are known to us. So basically, this is what we did so far. So from this, you'll have to proceed further to find your reaction rate for different scenarios. This is just when reaction rate or desorption can be rate limiting. So you can have a case where adsorption can be rate limiting and your reaction rate and desorption could be in equilibrium and so on. So all those cases we will try to look into in the next class. So we'll stop here for now. But before you leave, I have an announcement to make. So just stay put for a minute.